Thank you everyone for joining in. Welcome to OpalRT's webinar on microgrid controller testing with hardware in the loop. We have three specialists on this subject today with us. Myself, Syed Qasim Ali. I am the TND DER team leader in the access division at OpalRT. And I'll talk about the microgrid control systems and HIL test beds with the microgrid control systems, their architectures and different setups that could be set up for testing. Our special guest, Brian Miller, the microgrid strategic team leader at National Renewable Energy Lab, NREL, who will present the microgrid research capabilities, including multiple hardware in the loop testbeds. And he'll also show an overview of Borrego Springs controller hardware in the loop and power hardware in the loop test setup and results. We also have the participation of Scott Manson, who is the Engineering Services Technologies Director at Schweitzer Engineering Laboratories, SEL. During this webinar, Scott will present the latest developments with SEL's microgrid controls and that continue to successfully expand new microgrid research capabilities. This is the webinar outline. We'll each have our part of the presentations, and in the end, we have a question and answer period. You can start sending your questions, and we'll try our best to answer most of them in this webinar. If we are not able to answer them, we'll definitely answer them by email after the webinar. So I'll start my presentation with the typical V diagram, the V cycle diagram of product development, which I have adopted for microgrid development. So typically we start with gathering requirements for microgrids that would be obtained from the planning phase, which includes cost benefit analysis, definition of performance metrics, and of course technical standards such as IEEE 2030.8.7 and the IEC standards that talk about microgrid controllers. The second step you move on to is concept and system modeling. The third step is design studies, which will include modeling control, building virtual models for control and protection, doing grid impact studies, doing energy management studies, DER integration studies, grid code compliance studies, and of course KPI evaluations or performance metric evaluations based on the metrics that you defined in the first phase. Then, of course, you move on into real-time implementation, which would involve decoupling the model that you did that was optimized for offline simulation. You would decouple the model so that you make sure it runs real-time. If needed, you'll have to decouple it into multiple cores, into multiple time steps. That includes multi-rate modeling and hybrid modeling. It may also be multi-domain modeling for which entails hybrid modeling. The next step would be unit hardware in the loop testing. You would test each and every asset in the microgrid individually as if it was not connected to the whole network. The next step is integrated HIL testing, where you would test the whole microgrid or each and every DER as part of the whole microgrid. And of course, the final step is integrated verification validation, where you'll test all the test scenarios with a microgrid controller and finally validate all the KPIs that show you the performance of your whole system based on the performance metrics that you designed that you decided in the requirements. The second and the third step could be achieved using offline simulations, although you can get benefit of speeding up the studies, especially the design studies, if you use real-time or accelerated simulation in this step. Next, I'll show you two test beds, possible test beds. One is controller hardware in the loop, where we are able to test different levels of control functionality of a microgrid control system. So the microgrid itself would be modeled and simulated on the cores, and you'll have the first level of control, which includes control and local control and protection devices. You could either simulate those local control and protection devices or have an actual hardware of control and protection device connected to the real-time simulator. Then you can also test level 2 functions, which include the transition handling of a microgrid controller, of a microgrid by a microgrid controller and the energy dispatch function. Again, you could have a simulated microgrid controller or an actual microgrid controller that connects to the real-time simulator and then controls each individual asset and DER on the microgrid. It's also possible to test level 3 functions, although you won't really simulate those level 3 functions on a real-time simulator, but you can use communication interfaces provided by a real-time simulator to connect to either an aggregating agent, a market and price forecasting agent, or the weather forecast provider to allow optimization of the operation of your microgrid. Another type of typical test bed would be a power hardware in the loop test bed, where you can actually exchange power from the device under test and the simulated system. The way you interface your simulated system to the actual system is using either a switching amplifier or a linear power amplifier. Okay, so the typical studies that you would do based on these hardware in the loop test beds would involve either fast transient HIL, control and protection HIL, or large system dynamics slow HIL studies. So the first one, fast transient HIL, is mostly you're interested in studying switching harmonics, controller interaction, system power quality of each individual DER. Over here, the challenge is really accurately simulating power electronics, which may go to switching frequencies up to 5 kilohertz or maybe higher than that. And to simulate those systems, you need time steps that are in order of 100 of nanoseconds to about 50 microseconds. We've got some tools that allow you to go to hundreds of nanoseconds. It's EFPGA-SIM. And then typical EMT type simulations are done using eMegaSim RT-Lab and HyperSim from OpalRT. You could also have hybrid simulations where you decouple the system or the power electronics in EFPGA-SIM and run the whole system in eMegaSim or HyperSim. The next type of studies that you will be interested in is protection and control studies. The typical time step that you need for these kinds of studies ranges from 10 microsecond to 100 microsecond. You can typically study islanding protection, stability of the microgrid, cascaded events, protection coordination, and different applications over here. Then you may be interested in large systems and slow dynamics hardware in the loop testing, where you test the microgrid or a microgrid or clusters of microgrids in a large power system and study if they help or if they are able to provide grid services using an aggregator, for instance. It's also possible to run to simulate large distribution networks with three-phase unbalanced networks at when you're trying to study slow dynamics. Our tools, eMegaSim and HyperSim, again provide you EMT type simulation platform, but we also have ePhaserSim where you can do phasor domain simulation, be it balanced or unbalanced, and it really helps you run the systems real time if you are interested in studying large distribution systems. We also have in HyperSim, the HyperSim suite, it also offers you test automation, where you can get your parameters and test scenarios from the standards that define testing of microgrid control and control systems. You can provide them in an Excel file. TestView automatically reads them from an Excel file and then runs the simulation in HyperSim. Uses ScopeView to record and generate waveforms. Record waveforms from the running simulation. Does post-processing, and you can generate reports in Excel It may be pass-fail reports, it may be different performance indicators that you may be interested in, and have an automatic report generation using these tools. This slide shows the microgrid, the customers that we have that are involved in microgrid controller or microgrid operation testing or research. We have a presence all over the globe. So I'll show you a demo that we have of a microgrid. It allows you to interact with the microgrid that's running on a real-time simulator in real time. This is a good panel that shows you how systems react to different impedances that you provide the microgrid. But you could also automate this, and this shows a good example of how testing can be done. So, for example, this microgrid is part of a larger 600 node distribution network. It has a battery energy storage system, a wind turbine, a PV array, and a few different kinds of loads. It's all controlled by a microgrid controller that implements two main functions of the microgrid controller. It's not a complete controller yet. We're just demonstrating two functions. One is planned islanding, and the other one is energy or power dispatch, ensuring a reference power that either injected or pulled, absorbed from the main grid. So right now we are at -6 kilowatts absorbing, injecting power. We can increase this reference to maybe 4 kilowatts, and we can see the battery energy storage system dispatch changed to respond to this. We can also provide different disturbances like load changes and see how the system reacts. We also provide, we can also reduce the wind speed, so the wind power goes down. We can slow down we can reduce the irradiation and see how the power reduces. So if we want to do planned islanding, we request islanding event, and we see the power over here reduces down to 0. That's what the controller does, and then the controller opens the breaker, and now we are running in islanded mode. We can also run different kinds of studies. For example, we can have a definite load profile, an irradiation profile, and a wind profile, which we can see over here. And we'll see once we activate that, it starts reading the irradiation, the load, and the wind speed data from a recorded previous day, which was taken from California ISO, and then we can see how the system performs, especially the battery energy storage system dispatch. I'll shut down the profiles here. We can also perform fault studies. For example, we can have a 3-phase to ground fault on one of. So right now we are seeing the 3-phase to ground fault on one of the nodes in the distribution network, and we can see how the battery storage system responds to that fault. So the fault results in a voltage sag on the microgrid, and therefore the current increases to maintain power, output power from the battery energy storage system. So another thing that we have over here is that we are simulating the power electronics of the battery energy storage system on an FPGA that runs at 1 microsecond time step, while the whole network runs at a 50 microsecond time step. With that, we can actually see the ripples on the current of a battery energy storage system, whereas the rest of the DERs will show you nice clean waveforms, because they are average model converters used to implement them. But for the battery energy storage system, we can see the current has a lot of ripples on them.